We said that the average speed of molecules in a gas at a room temperature is actually a few hundred meters per second. But we know that gas doesn't just zoom from one side of the room to the other. So what we're going to do is now think about what's going on in a detailed path of what those molecules do. We call diffusion the process of a molecule going from one position to a final position that goes through what we call a random walk. So we say that it diffuses from here to there. It does not go in a straight line. It moves in small straight line segments, but then it has collision. These collisions change the direction and possibly the speed. Though later when we talk about some collisions, we'll be calculating it without speed changes. And the other thing to remember is that it really is moving freely in this straight line. So if you think about a ball moving through the air, you might say, well, yes, it moves in a straight line if we neglect gravity in between people hitting it or it hitting a wall. But remember that the ball has air resistance. Here, we are literally talking about molecules of air. So these straight line paths, we don't have to worry about air resistance because we are in fact talking about air itself. Now, we neglect gravity for all of this, and that's something that is a little easy to motivate here. Again, we say that the distance it's traveling here is very short, and we're going to calculate what that is. That will be a big part of what we're doing. But now think about the speed. This is a few hundred meters per second. So if these time increments are, say, nanoseconds, how much would the velocity have changed or the position have changed due to the acceleration of gravity in only a few nanoseconds? Not very much. So we're neglecting the effect of gravity, not necessarily because gravity, the force is small, obviously the mass of these are small, but also because the time intervals here are so short that the acceleration has a very small effect. So that's one way to think about this and why we don't worry about gravity. So the definition of mean free path is the total length that it's traveled divided by the number of collisions. So total distance divided by number of collisions gives you mean free path. So this is just the average distance between collisions. Sometimes it's very small, sometimes it's a bit larger. That's fine. Everything we're talking about now happens somewhat randomly, and there's going to be a distribution from small to large, but there's some average in between, so we can calculate that based on distance divided by number of collisions. Now, this isn't a particularly helpful formalism. It's okay, but we can do a little bit better and actually try to relate this to the speed that our molecules are moving, and that's what we're going to do now. So in order to do this, we need to think about some geometry here. And our molecule traces out some path, and we can think about a little cylinder around it that kind of relates to the radius of the atoms themselves. And where this comes from is that if the centers of them are 2 radii apart or closer, they're going to collide. But if they're farther than 2 radii, again, we're talking about the centers, then they can pass, that there's no collision. So the radius of the cylinder we're thinking about actually is 2 radii, because we don't just care about the radii of the molecule that's moving through, but we also think about the radii of the molecules it's going to hit. So that's how we're going to think about mean free path. We want to ask, how many collisions is it going to have as it travels? And these collisions are going to be determined by the size of this tube that it's tracing out. So now let's do this mathematically. First, we're going to assume that there's an average density of molecules. Now, obviously, in the gas, some molecules are closer together and some are farther apart, but that's fine. We're just going to assume one value. Now, this might look like we're assuming a uniform density, but really you can just think of it as an average density. So this is the number density because it's just the number of molecules divided by the volume. This isn't the specific number in the path or the volume of the path. This would be overall of our gas. So this is one of our macroscopic parameters we already thought about. As I mentioned before, the number of collisions are going to be given simply by the number of molecules along the path that are in the way, really. And we can figure out the number of molecules simply by taking the volume of the cylinder that molecule was tracing out, where again the radius was given by 2r, and you then are using kind of a bent cylinder, and multiplying it by the density. So we're saying what's the volume, what's the density in that, that will give us our number of collisions. So again, that volume is going to be the area of the end, where again our radius is actually 2r, and then the length. Now, obviously it's going to be bent in pieces, but we can think about the total length as effectively grabbing it and stretching it out, so we don't have to worry too much about that. And remember that our original definition of mean free path, lambda, was the length divided by the number of collisions. So this is the same length. Now the book points out that this argument here is a little bit hand-wavy. So when we do it out, where again the length before was on top and the number of collisions were on the bottom, and now we've multiplied this volume, so the L canceled, by the number density, and well, there's this weird like square root of 2 that appeared, and the book says, well, yeah, don't worry about it. And again, a more rigorous derivation of this is beyond the scope of this class, but it does appear in Physics 210 if you continue on. So the main takeaway here that I want you to understand is before we just define this by total length divided by number of collisions, but we now made an argument based on microscopic properties regarding the volume of the cylinder and one of the macroscopic properties to now actually get the mean free path in terms of something we know. In this case, the number density and then the radius of our molecule. And again, that's something that you can just estimate the order of magnitude based on what type of molecule it is. So now we can just take the mean free path in terms of other things. Note that the mean free path is independent of the speed. It's independent of the temperature. So this is going to be something that we use later. We see right now that the mean free path is an independent parameter that only depends on the size of our molecules and their number density. So obviously the number density can change if your volume's changing, but this is independent of temperature, speed, and everything else. So later we will use that, and that will be helpful, but this is an interesting result.